Okay, welcome my dear students. Again this class, last class we discussed some problems related to the isomorphism or inverse linear transformations. When we discuss some problems where we show that some of them, one of the example we show that how to find the inverse of a linear transformation. So if we have to first show that is a non-singular. Non-singular means if is 1 1 and on 2, and then we have to show that is a how to find the inverse of a linear transformation. Okay, in this class we discuss some important related properties of a invertible linear transformation. Then let us begin with the result. This is T from let T from V to W be an isomorphism of a two vector spaces. Is isomorphism means we have simply say that is a non-singular, and that is means this is a two things is there. This is means this T is you have a 1 1 and T is on 2. So, this linear transformation T is isomorphism non-singular transformation of two vector spaces. Then if V 1 V 2 V n are linearly independent vectors in V, then T of V 1 T of V 2 up to T n are linearly independent in W. Next is if T V 1 V 2 V n is span of a V, then T of V 1 V 2 V n is a span of a W. And now if we form a basis for V, then this is T of V 1 V 2 V n up to form a basis for W. And in the last one is the dimension of a V and dimension of a W are the same when these two linear transformation is a isomorphism. We start with the first one. Let V 1 V 2 V n be an linearly independent vector and T of V 1 V 2 V n are independent. So, first we try to prove that this T of V 1 V 2 V n are linearly independent. So, this means we write alpha of T of V 1 alpha 1 alpha 2 T of V 2 plus so on alpha n T of V n is equal to 0 vector. 0 vector V, and now because T is you have a T from V to W is you have a linear and also 1 1 and on 2. So, this means T is linear, this can be written as a T of we have a alpha 1 V 1 plus alpha 2 V 2 and so on. We have a alpha n V n is equal to 0 vector. And now this implies that you have a given in the form of this is T of alpha 1 V 1 plus alpha 2 V 2 and so on. You have a alpha n V n is the element of a kernel of a T. And now because you have a given T is one linear transformation, this implies that kernel of a T is equal to 0. So, this means this implies that we can say that alpha 1 V 1 plus alpha 2 V 2 plus so on alpha n V n is equal to 0, and because V 1 V 2 are linearly independent. So, this implies that if this thing is equal to 0, then all the this is the trivial linear combination, means all the scalars are is equal to 0. So, this implies that alpha 1 is equal to alpha 2 is equal to alpha n is equal to 0. So, we start from our definition from alpha 1 T of V 1 plus alpha 2 T of V 2. Alpha n T of V n is equal to 0, and we have to show that if this is equal to 0, then all the scalars are is equal to 0. So, this means clearly say that T of V 1 plus T of V 1 T of V 2 up to T of V n are linearly independent vectors in W. So, okay. So, this means we have a independent if this is equal to 0 in W, then by the linearity I just take a linearity and then T is 1 1. So, we calculate that this is equal to since V is equal to 0. So, this is linearly independent, thus this is equal to 0, we have a this is equal to 0. So, because T is a 1 1. So, there is a two way we can just say that this can be I use the I explain you by the using the kernel, because kernel of this, and also you can use this property of T of u, because 0 can be written as a T of 0. So, T you can also write this is also the element of a T 0 and T is 1 1. So, this is equal to same as a u is equal to V. This also we can using into this form, but in any way you can use this if this thing is equal to 0. This is also true. We just say that this alpha 1 V1 plus so on, alpha n Vn belongs to the kernel of a T, and now you know that the T is a 1 1. So, kernel of a T is equal to, you have a 0 subspace. So, this is equal to 0. That is both ways is true, either use the 1 1 because we have to using the 1 1 ness. So, this is equal to 0. So, T V1 V2 V are linearly independent. So, this means all the scalars are 0. So, if all the scalars are 0, then this is equal to 0 implies that the T of V1 plus T of V2 and up to T of Vn are linearly independent in a W. Okay, so now we have to second part is if V1 V2 Vn be a span, then T of V1 T of V2 up to Vn is a span of a W. Because we have a given T is on 2, so V1 V2 Vn is a span, V1 V2 Vn is span of a V, and W belongs to W since T is on 2. So, there exists a vector V, T of V is equal to W. So, T of V is equal to W means V is an span of a this. So, we have a any vector V belongs to V. So, this V can be written as a finite linear combination of the elements of the span of a as this V1 V2 Vn. So, this V can be written as a alpha 1 V1 plus alpha 2 V2 plus so on alpha and Vn. And now, because W is equal to W, you have a W is equal to, you have a T of V. This can be written as a T of, we have a alpha 1 V1 alpha 2 V2 plus alpha and Vn. And now we have a given T is a linear map. So, we can write alpha 1 T of V1 plus alpha 2 T of V2 plus so on. We have a alpha and T of Vn, and that means we can say that clearly W can be written as a finite linear combination of the elements of a T of V1 V2 Vn. So, if this can be written in the form of a T of V1 V2 Vn. So, this implies that we can say that the span of T of V1, T of V2 up to T of Vn is equal to W. So, we can say that this completes the proof of this. So, T1 T of V1 T of V2 up to 2V of Vn is span of the W. So, this completes the second part of this proof. So, this means we can just say that as a linear combination of this. So, now we have finally if V1 V2 Vn form a basis for V. So, this is clear by the definition. If V1 V2 Vn form a basis of a V, so we can say that span of V1 up to Vn is equal to V, and we have a V1 V2 up to Vn set is linearly independent. And now the part 1 we have to show that if V1 V2 Vn is linearly independent. So, if we have a proof already that this case is a set V1 V2 up to Vn is linearly independent in V, then T of V1 T of V2 up to T of Vn is linearly independent in W. And also we have to prove that if span of V1 up to Vn is equal to V, then by the part 2 we can show that the span of T of V1 also show that T of V1 T of V2 up to T of Vn is equal to W. We have a proof that T of V1 V2 Vn is a linear independent W, and span of a T of V1 is equal to W. So, this implies that we can say that we say that T of V1 T of V2 up to T of Vn is a basis for W. So, this completes the proof of the third part. We have to show that if we have a T from V to W is a linear and one non-singular linear map, then if V1 V2 Vn is a basis for V, then T of V1 V2 Vn is the basis for W. By the using the part 1 A and B, we can complete the proof of this result. Since suppose this by A, V1, V2 are linearly independent in W, and by B, this is a span of a W. So, this is a form a basis of a vector space of a for W. And now we have to move to the last part. Last part is a third part is dimension of a V and dimension of a W. In the previous part, we show that the V1, V2, Vn as the basis of a V. So, then that element in the basis is a n. So, this means dimension of a V is equal to n, and we show that the T of V1, V2, Vn are the basis for the dimension basis for W, and also there is a elements are n. So, this is also is a dimension of a W is also is equal to n. So, we can say that the dimension of a V and dimension of a W are the same. So, if dimension of a V is equal to n, there are some basis say V1, V2, Vn for V with n element, and if this is a basis for a V1, V2, Vn, then by the C part we can say that clearly T of V1, T of V2, T of Vn is a basis for W with n elements. So, we see that T of V1 is T of V is equal to T of W. So, this complete the proof of a complete theorem. So, this means we share this is the 4 parts of this theorem. If V T from V to W is a linear non-singular linear transformations, then we say that if V1 V2 is linear independent in V, then T of V1 image is also linear independent in W. If V span of a V1 V2 is a span of a V, then T of V1 V2 is span of W. Similarly, combine these two A and B part, we can say that if V1 V2 and basis for V, then T of V1 T of V2 T and is basis of a W, and also the dimension of the V and W are the same. So, this means clearly we can say that when we have a linear transformation which is non-singular, then clearly there is a dimension of both the V and W are the same, and also if basis of the V and then there is a number of element in the basis does remain the same. So, if we have to this theorem, now we have to prove the main one more theorem. This result is say that V and W be a 2n dimensional vector space. Because of the real vector space, I take a real. So, then V and W are isomorphic. So, this means we clearly say that if we have a V and W are n dimensional vector spaces, then V and W are the isomorphic. So, first we take a V and W be n dimensional vector space. So, we have a assuming the proof by the basis element. So, let B is equal to V1 V2 Vn be a basis for V, and W1 W2 is the basis for W. And because then there is a linear transformation T from V to W such that T of Vi is equal to D of for a linear transformation T from V to V a linear transformation. Let V and BW be a two linear n dimensional real vector space, then V and W are isomorphic. So, we define a let T from V to V a linear transformation. Okay, so if linear transformation, then for this is the clearly we have to prove T of Vi is equal to there is a unique image T of Vi is equal to W of I. Now we show that V and W are isomorphic, so we have to show that these are the map defined. Show that first is a T is this map is defined is 1 1, and also we have to show that this map defined is onto, and then is a non-singular. Then we can say that is it is a non-singular, then this is a clearly is an isomorphic. So, first we show that T is 1 1. So, T is 1 1 means we have to suppose there exists some V belongs to V, and V either we have to T of V is equal to 0. Now, because V1 V2 Vn is the basis for V, and we have a some V is the element of this, so V can written as a V can be written as a finite linear combination of the element of the basis. So, alpha 1 V1, alpha 2 V2 and alpha 3 V3 plus so on alpha and Vn. Now, we can take a T of V is equal to we have a T of alpha 1 V1 plus alpha 2 V2 plus so on alpha and Vn, and now T is we have a linear map. So, we can say that alpha 1 T of V1 plus alpha 2 T of V2 alpha and T of Vn, and now T of V can be written in this form. and so we have to just say that this t of v is equal to 0. We assuming this t of v is equal to 0, so this can say that this is equal to we have to 0. So this implies that we can say that this vector is equal to, or we can just simply say that this is equal to t of v is equal to 0, or another way we just try into this way also, because t of v is equal to 0, so we have to leave it here. So 0 is equal to t of v, or we just we have to just say t of v is equal to 0, then v is also is equal to 0. So these are the basis vectors. So now we have a basis vector. So this linearly independent, all scalars are equal to 0. Okay, just try to one another way, which assuming v is the element of a suppose kernel of a t, and then if is a kernel of a t, this means t of v is equal to 0. If t of v is equal to 0 means this is v can be written in this form. So t of v can be written in this form. So this means t of v is equal to 0, and this means t of v is equal to 0, then alpha 1 v1 plus alpha 2 v2 plus so on. We have a alpha and vn is the element of a kernel of t, and if this element of the kernel of a t, then we can say that if this means this is but t, this is the element of a kernel of a t. So we can just say that this is we show that this is v is equal to 0. So this v is equal to 0 means we have to take v in this form, and then alpha t of v1 v2 vn, and this is w1 w2 wn. We write the values of a t of v1. We can sequence that t of vi is equal to, we write is a wi. So t of 0 up to this, we can write alpha 1 t of vn is w1 w2 wn. Now this is equal to 0 for all this is w1 w2 w2 and is equal to 0. So w1 w2 is a basis for w. So this means must have all alphas r is equal to 0, and then v can be written in the form of a linear combination is equal to 0 vector. So we show that dv is equal to 0 implies that we have a v is equal to 0, because whenever v is equal to 0 means we t of v is equal to t of 0, the v is equal to 0. So this means we can say that clearly t is this v is the element of a kernel of a t. So this means tv is equal to 0, v is equal to 0. This means kernel of a v is nothing but is equal to, you have a 0 subspace. If kernel of a v is a 0 subspace, and hence t is a 1 1, and hence t is also on 2. Why? Because dimension of a v and w are the same. So we can say that clearly this show that v and w are isomorphic to each other. So this means we can just prove this because I use the property of a t of 0 is equal to 0, and also we have just said that we can take a t of v is equal to t of 0, and then we have to ultimately show that v is equal to 0. So this means by this we can say that t is 1 1, or we can say that whenever tv is equal to 0, v is equal to 0, v is the element of a v. So tv 0, v 0, only the possibility is a kernel of a t is only the 0 subspace, and then we can say that clearly if 1 1. So by the, because the dimension of a v and dimension of a w are the same, so by using this theorem, when both the dimension are the same, t is 1 1 if and only if t is on 2. So t is also on 2. Now this show that v and w are the isomorphic. In general, we can say that if v is a dimensional real vector space, v is isomorphic to Rn. This I already explained you in the, when a coordinate vector, we take any linear transformation t from vector space to Rn is always is a isomorphic to, is a non-singular, we can just say that is called as a natural isomorphism of this linear transformation. Okay, now we just try to find one more example in this case, and we conclude this session today. By this example, we try to find whether this is a non-singular or not. So I just try with the first is with the is a kernel of a this. We have to take a kernel of a t is equal to is 0 or not. We just take a so we by using t of v1, v2, v3 is equal to, we have to 0 0 0, and then because both the dimension are the same, so it is enough to for a non-singular, it is enough to show that T is 1 1. Okay, so this is defined in the form of this V1 plus V3, and then this is V1 plus V2 plus V3, and then this is V3 is 0 0 0, and this implies that you have a V1 plus V3 is equal to 0, and then you have a V3 is equal to 0, then you have a V1 plus V2 plus V3 is equal to 0. From V3 is equal to 0, this implies that by this you can say that V1 is equal to 0. So V1 0, V2 0, so this is 0, this is 0, this sorry, this one 0, this one 0, we can say that this implies that V2 is equal to 0. So ultimately we can say that clearly, this is okay, this is clearly we write into this form. So this is this form. So solving these three equations, we get V1, V2, V3 is equal to 0. Okay, so this we can show this is equal to 0 means we can say simply is equal to kernel of a T is equal to 0, hence T is 1 1. And now because T is 1 1, because we have a dimension of a V is the same as a dimension of W. Now, since a dimension of a V is equal to dimension of a W, now we use the result when T is 1 1, when both the vector space is the same dimension, T is also onto. So this means we can say that T is also onto, hence T is a non-singular and T inverse exists. Okay, now we try to find the T inverse. So we take a T inverse W1, W2, W3 is equal to this form, and now we have to V1 plus V3. So this can be written in the form of a T of V1, V2, V3 is equal to, we have to write is a W2, W3, and now this is defined in the form of a V1 plus V3. So you have a V1 plus V3. Now we have a V1, V2, V3. So we have a V1 plus V2 plus V3, and then you have a V3 is equal to W1, W2, W3, and this gives you have a, by the equation we have a V1 plus V3 is equal to W1. Now we have a V1 plus V2 plus V3 is equal to W2, and now we have a V3 is equal to, you have a W3. Now by simplifying this, we getting V1 is equal to, you have a W1 minus W3, and then V3 is equal to W3, V1 is equal to W1 minus W3. So we get this substitute here. So we get a V2 is equal to W2 minus V1 minus V3. So you have a W2 minus V1 is equal to, you have a W1 plus W3, V3 is equal to minus W3. So this is nothing but is equal to W2 minus W1. So we can say that, substitute the value for here. So we can say that T inverse of W1, W2, W3 is equal to V1, V2, V3. So V1 is equal to, you have a W1 minus W3. V2 is equal to, you have a W2 minus W1, W2 minus W1, and you have a V3 is equal to, you have a W3. So this means this we can just say that we find the inverse of a T inverse W1, W2, W3 is equal to, you have a in the form of a V1, V2, V3. So this clearly we can say that into this form, this find the linear transformation. So inverse of a linear transformation into this form. So we have a in this form. Now we have to substitute the value. Now we have clearly simplify this, and then we have V1 is equal to this, V2 is equal to this, then T of inverse is equal to this is equal to this thing. Okay, so this complete the solution of this problem. Now I have to just one more problem, just try to find the is a non-singular or not, and then we try to find this is the map is a non-singular. Show that this map is a non-singular because is a again P2 to P2. So we have to just it is enough to show that this map is a we have a clearly is a kernel of this is equal to 0. So, kernel of a t is equal to 0 means we have a naught plus a1x plus a2x square is equal to, we have a 0 polynomial. So, 0 plus 0x plus 0x square, and now this map is defined in the form of this a naught plus a1 plus a1 plus twice a2 plus a naught plus a1 plus 3 of a2 x square, x is equal to, you have a 0 0x square. Now, this gives you have a naught plus a1 is equal to 0, a1 plus twice a2 is equal to 0. Now, we have a naught plus a1 plus 3 of a2 is equal to 0. Now, we have to first and last we gives the a2 is equal to 0, then we have to just is equal to, we have some 1, 2 and 3. From 1 and 3 we have a given a2 is equal to 0, and now from 2 we can say, now from 2 we can say that a2 is equal to 0, a1 is equal to 0. Now, from 1 we can say that a naught is equal to 0. So, ultimately we have to show that clearly, we have to show that we have a naught is equal to a1 is equal to a2 is equal to 0. That means, kernel of a t is equal to, we have a 0 subspace. This implies that t is, we have a 1 1, and also we have a dimension of a p2 is the same as a dimension of both the vector space are the same. So, by the result, this implies that clearly t is also is a onto, and then we try to find what is the inverse of this linear transformation. So, okay, we try to find the inverse. So, we have to find the t inverse of, we have a this map of this. We take a t inverse of this map is equal to, we define a t inverse of we just take a t inverse of a naught a1x a2x square is equal to b naught b1x b2x square. Then we have a t of b naught b1x b2x square is equal to a naught a1x a2x square, and then by the definition this can be written as a p naught b naught plus b1 plus b1 plus twice b2 x plus b naught b1 3 b2 x square is equal to a naught a1 x a2 x square. Now, this can be written as a b naught plus b1 is equal to a naught. Now, we have a b1 plus twice b2 is equal to, you have a a1. Now, we have a b naught plus b1 plus 3 b2 is equal to a2. Now, simplify these in the terms of we have a b naught and b3. So, this means we can just take this thing. So, this means first and 3 b3 b2 is equal to a2 minus a naught. So, b2 is equal to 1 by 3, you have a2 minus ka a naught, and if b2 is equal to, you have a this, so you have a b1 is equal to, you have a a1 minus 2 times of a b2, and this can be written as a a1 minus 2 by 3 a2 and minus this is equal to, you have a minus ka b2. So, minus minus plus 2 by 3 this is b2 is equal to is equal to a naught, and then we have a b naught is equal to a naught minus b1 is equal to a naught minus b1 is equal to, you have a 1 by 3 a2 minus a naught, and then you have a simply is equal to, you have a 3 minus 2 by 3, this is okay, just we have to simplify more. We have a b1, okay, sorry, b1 is equal to, you have a this, sorry, we have to, from this we substitute here, we write the value for b naught is equal to a naught minus b1, a naught minus ka a1 plus ka 2 by 3 a2 plus ka 2 by 3 a naught, and this is equal to 3 plus 3 plus 2 is equal to, you have a 5 by 3 a naught minus ka a1 plus ka 2 by 3 a2, and then we have to substitute the values of all this. So this is okay, this is clearly a2 minus this is a naught a2 minus 1 by 3 a2 minus b1 is equal to clearly here, and now we substitute b1 is a1 minus 2 times of a b2. So 2 by 3 a2 minus this is clearly is correct, and now we substitute b naught is equal to a naught minus a naught minus b1, b1 is equal to, you have a1 minus a1 plus, and this should be minus, sorry, okay, so this is minus, so this should be the change, and this minus means this should be the change, this should be is equal to 3 minus 1 is equal to 1 by 3 a naught minus ka a1 plus ka 2 by 3 a2. Now we have to substitute the values of a b naught here. So we get substitute here the values of this b naught, b1, b2, b3. So this can be written here. B naught is equal to, you have a 1 by 3 a naught minus ka a1 plus ka 2 by 3 a2. Then you have a plus b1x, b1 is equal to, you have a like this, you have a a1 minus 2 by 3 a2 plus 2 by 3 a naught x, and then plus we have a b2 is equal to, you have a simply is equal to, you have a 1 by 3 we have a 1 by 3 a2 minus a naught x square. So T inverse we can write into a this form. So T substitute we calculate the value for b naught, b1, bx, b2 x square. Substituting this value into this, so clearly we have to getting this here. So this I just complete this solution of this problem. Now I just stop today's class at this point. In the next class I have to define the LU spaces. L of UV means homomorphism of two spaces. We take a two linear spaces, collection of all the linear transformations. How to discuss is a linear collection of all the linear transformations. So in the next class we discuss about the L of UV spaces, or is also called as a homo of UV spaces. So at this point today's class is I stop with this problem. With this problem we have to find the inverse of a this polynomials where P2 is defined into this form. It clearly is a non-singular, is a 1 1, and also because of the both the dimensions are the same, so it's onto, and we have to find the inverse also. So thank you very much for at this point, and in the next class we discuss about the LU space. So thank you.